But now I want to tell you that engineering design is not the same as the scientific method, because its purpose is different. And now you can see why there was a clash between finding causes and finding cures. You can see that in the early Greek attempts, they were trying to do something like engineering design, find a cure for a particular disease. And so then there were people who were looking at causes and people who were looking at cures, and we are looking now at cures. So up to now we were talking about causes and things like that, how to acquire knowledge. Now how to utilize knowledge is what engineering design is about. So let's talk about what's the differences. Science, and I'm acquiring a way to acquire knowledge, construct shareable, coherent, comprehensive descriptions of the universe in a verifiable manner. So not everything, but it has to be that aspects of the universe which is reproducible in some way. Engineering is a very different task, a way to identify societal needs, mostly physical societal needs. We're not talking about mental or intellectual needs of society, that's a separate thing. Most of engineering is focused on physical societal needs and recognizing constraints and construct products and processes that will address them. Right? You can see it's not the same as science. Okay, that's what engineering design is about. So for engineering design, tools are experience. That is, remember the empiric school of knowledge, which says cause is not the same as cure. Right? So then many times you have to do experience. Sometimes you have to do knowledge, and knowledge about reproducible aspects, because some aspects of engineering are not within the reproducible domain, because you have to deal with individual items, not collective groups. So sometimes if you're building something one-off, it's not going to be repeated. So it's not always that you can use science, because science is about repeatability, whereas engineering is not necessarily about that. So that makes it slightly different. The basic idea is we have to be able to do quantitative decision making under uncertainty in input, state of the system, outputs, what is the system, all of this are uncertain. And yet, even if we lack knowledge, we still have to make decisions. We cannot wait for perfect knowledge. So this is what makes engineering design somewhat different from science. Okay, so how does that work? First step is identify what is the societal need and what are the constraints. For this, you need the same kind of things that you need for observation. You need empathy, you need curiosity, you need serendipity, you need mindfulness. So this is the first identification of societal need. Who knew that what society needed was 44 characters or whatever it is for Twitter? Right? So that requires some level of serendipity, some level of curiosity, and some level of mindfulness to recognize that that was a societal need. Right? So that kind of thing is what I'm talking about. So that leads to quantify these needs into specification. So this requires craftsmanship, it requires knowledge, it requires empathy, it requires holistic view, and it requires balance. Because all of these kinds of needs and constraints, there is always a trade-off, and so you have to be aware of the trade-off. So that requires balance. Okay, so once you have quantified it into specifications, and by the way, notice that the arrows don't go only one way, it goes back and forth, because there's loops within loops. So you do some specification, then go back and see if that's really what is the need. If that's not, come back and do more specification, that kind of thing. Okay, that leads to both the needs and specifications, leads to identification of functionality. What should the product or process do? This is different than what should it look like or what should it be. So if you think about a cell phone, for example, initially people thought, where should I put the keyboard? That keyboard is what it should look like. It was only Apple who said what the cell phone should do is accept input, not provide keys. Suddenly what happened is the keyboard disappeared. If you remember BlackBerry and other things which were full, there were a lot of keys and then thumb typing and all of that. Now you can see there's a virtual keyboard. right? So that's a way of thinking about what something should do and not what something should be. Once you have done that, this requires abstraction, creativity, reasoning, all kinds of things. And then you have to identify and figure out how to make a physical object or a physical process that embodies this functionality. So now this is a challenge, and that requires you to know something about the specifications and functionality and all of these things. And this requires creativity, belief in order, boldness, scientific knowledge, codified experience, etc. This is what is meant by skill. Okay. Then you come to the next stage, which is testing what you have embodied against specifications. So this is, you have to have skepticism and attention to detail. Then the next thing to that is to refine and modify, and it requires creativity and boldness and so on. You can see that this part, identifying required functionality, embody the functionality, test against specifications, refine and modify, this is very similar to the scientific method, but it's not the same as the scientific method. It's similar, very similar. The question of identifying needs and constraints and quantifying it into requirements are outside this, as well as converting the needs and constraints into functionality is something that's outside the typical scientific method. Okay, so there are some things that are similar, there are some things that are different. This is what engineering design is about. What we are doing when we talk about modeling in an engineering class is helping this process, not the scientific method, but helping the engineering design process or quantifiable design decision making. That's what we are trying to do. So let's look at a particular example, and then it becomes clearer. So typical problem, let's say you're trying to design a bracket. Here's the bracket, something that looks like this. This is what you want to design. You want to ask a bunch of questions about this. You want to find out structural safety. Given some estimated loads on the bracket, how to ensure that it is strong enough, that is, it should not break, stiff enough, should not misalign with other components, stable enough, should not buckle due to slight changes in the load and things like that. So that is strength, stiffness, stability. So that's part A, that's called structural safety. So you may want to investigate that. The second thing you may want to investigate is what geometry or material changes would be good or bad, i.e. which kind of changes in the geometry and materials would be good. For example, I may want to say, look, I don't want this kind of a corner, maybe I want to have a chamfered corner. Would that be good or bad? Or maybe I don't want steel here, I may want to replace it with aluminum. Is that good or bad? Right? So that's the question number 2. Question number 3, instead of a load being here, what happens if I apply the load like that? Is that good or is that bad? Will it still survive? So on. Then when you're doing failure analysis, you want to find out this one was put in service and it broke, and the company is saying it's a wrong bracket. Your company, the bracket company, is saying no, you did not use the bracket properly or you applied the wrong loads. Who is correct? So this is failure analysis. So there are 4 things: structural safety, parametric study, input variations, failure analysis, this kind of thing, and you want to be able to find out the answers to these kinds of questions. And the last item is simulations. I am going to put sensors to monitor this bracket. Will I be able to distinguish what will happen prior to failure? So before I mount the sensors and all of this stuff, I want to test and see whether it's a good place to put the sensors and what signal from the sensors means what. I may get signals, but the question is what signals mean what. So these are the 5 things that we want to do to help a designer. Okay. Now how do I do this? One way is extremely straightforward. Build and test. Okay. This is the data analysis, empiric school of knowledge. You can only gain knowledge by experience and history and analogy. So you build and test. And then you create a database and then you get the knowledge. That works. That's foolproof because you actually tested it. And this is what you might have to do if there is no other option. Why do we need other option? The reason is it's not easy, actually practically impossible to extrapolate for different materials, shapes and loads. It's not possible. Okay. It's extremely, even if it were possible, building and testing is extremely expensive and time consuming. The last item is it's impossible to test some things because of extreme conditions. You know, you may land up with very dangerous conditions which you may not ever be able to test. So, for example, if you wanted to figure out why did the World Trade Center come down, you are not going to be able to build another World Trade Center, instrument it, and crash a plane into it and try and figure it out. Not feasible. You got to now come up with some kind of a model that will do. Okay. The second approach, which works when this thing is problematic, is physics-based approach, which uses causality and constraints coupled with some tests and correlations. It is not a replacement for tests. It's a way to actually reduce the number of tests you have to do. So I need you to realize that it's not a replacement, it's just a reduction in the number of tests. And you should be able to answer the questions that we raised earlier, the 5 questions. Okay, and this procedure has been painstakingly developed over the last 300 years, more or less. And it's a reasonably successful approach. So how does this work? So before we go there, let's clarify it by looking at a specific example. So you want to predict the motion of the planets. The original idea was by Ptolemy of Thebade in the 2nd century AD, and this was an astronomical treatise, and it was based on Babylonian observational data. So this goes back a long way, and the Babylonians had observed very detailed motion of planets, and Ptolemy came up with a way to predict, and this was called the Ptolemaic epicyclic theory. So you can see that the Earth is in the center of this thing, and the motion of the planets are going around, and this is entirely based on observation. There is no model, there is no theory, there is no simulation, nothing. He just plots the thing and then tries to fit it with some curves. So this is entirely curve fitting approach, and it is remarkably successful, and it's called the Ptolemaic epicycle approach. An epicycle means cycle within a cycle, so circles within circles. So it's it looks like a gear system. So, and it was a pure data approach. Find a way to represent the observed path of the planets in the zodiac, and it was able to do that. Worked for more than 1,000 years very well. But it does not require any hypothesis about the cause of motion or even about the structure of the planetary system. Nothing. It just says here it is. This is the motion. This is the observations. I plot it and I try to fit it with some simplified. This is only a data reduction technique. This you can say as one of the first attempts at data mining. So that you can see something on this, right? So the thing is, the result provides no insight or predictability outside the setup. So if there was a new planet, you couldn't say what is it likely to do, because there was no cause. So you just wrote down whatever it was, and that's what it is, right? It's very efficient as long as you're within the range which you're talking about, and you can see it's extremely complex. So contrast that with Newton's law of motion and gravitation. So this was the next major step in this direction, and it worked by a very simple technique. It was called divide and conquer. So what you did was, don't look at the system as a whole, divide it into subsystems and use empirical correlations at the subsystem level, right? For that you have to have an idea of the fact that the subsystems, it is the interaction between the subsystems. So, and there's a very interesting idea of duality that runs through this whole thing. There is something which is called cause and something which is called effect, and we will see specific examples of this duality as we go along. So this is actually an idea or a principle that is not empirically verifiable, this idea of duality. I can show you that somehow this seems to work very well for the cases that we are looking at, but this is a principle that is beyond beyond empirical observation, empirical verification. Okay, so the idea behind Newton's laws is that motion are caused by forces, and the value of the force, this is the correlation. Value of the force is correlated to the distance between particles through the inverse square law. So this, whenever we say law, we mean some kind of correlation. Okay, so the empirical correlation is at the simplest subsystem level, pairs of planets, and is extremely simple. Right? Cause and effect is through Newton's laws. Assemble all the forces on the body from pairs and use laws of motion to then predict the motion of the body. So you can see that this is it turns out to be surprisingly effective, and it has unexpected predictive power. And the other thing that you want to realize is that complexity is not built in, but is actually emergent behavior due to the interactions between the subsystems. So even though the interactions are simple, complexity comes from large number of interactions, of fairly simple interactions, which gives you very complex behavior. But the problem is that as the system goes, behavior prediction becomes problematic, because now I have to assemble this complex system. I mean, the simple systems together to make a complex system. This assembly process can get out of hand, and you will get all kinds of funny things. Now small changes in how they interact and small changes in their starting conditions gives you large changes in the output. So that's the bad news for many of these things. So you have to be very careful. And the other thing which is a difficulty is that there is feedback. Emergent behavior influences subsystem response. What do I mean by that? So think about a very interesting cause-effect behavior, which is genes cause behavior. That's genes are 23 chromosomes, blah blah blah, and then you have all these genes, and then people can say you get angry because you have some kind of a genetic makeup that makes you angry, blah blah blah, all this stuff. The unfortunate thing is that people have also figured out that behavior affects genes. So if you are consistently angry, there are chemicals that are released that change the makeup of your genes. So now anger is not a subsystem level response. It's a fairly global response about a person, which affects at the genetic level. I mean, I'm just picking anger, but there are other things that work the same way. And in fact, I'm not making this up. You can go and look it up. In fact, stress actually changes genetic behavior in many ways. So you can go take a look at that. It's actually something that people have seen. So what happens is the emergent behavior influences subsystem response. So now you have some other feedback loop which is more complicated. So we struggle with this. Our current thought is that, look, you cannot go all the way to saying simplest model, which is called reductionist approach, where you say ultimately I don't want to dive down and say, okay, if I know what the quarks are doing, then I can explain everything else. The answer is no. So you have to actually balance simplicity of correlation and emergent behavior. So you have to stop it at some level and say, okay, below this level, I'm just going to use some kind of correlation. I cannot go below this. That's how models work now. If you divide too much, you'll have a tough time putting it back together. Think of it that way. Okay, and you may lose some very significant emergent behavior because you made some very slight simplification, but it gets magnified as you assemble more and more things. So that's a big problem. So let's look at how this works. So I have the structure, the bracket. You can see I have divided it into pieces. Each piece is supposed to have a simple response. So each piece, so this is a piece, and this is another piece. If the response of this piece and this piece are different, then it is inhomogeneous. That's how we define it. If the response of these two pieces are the same, or any two pieces are the same, then the body is said to be homogeneous. If the responses of any two pieces are different, then the body is said to be inhomogeneous. So by the way, this is at the level of your model for the body. What the body is a different thing, because remember, by the time I say that there are pieces, I'm already said it's some kind of a continuum and so on, so that's already a model. So please remember, homogeneity, inhomogeneity, all of these things are actually a characteristic of the model of the body and not the body itself. And then we have to characterize the response of the units. So we have to characterize the response of these pieces by doing tests. And then once I have the response of the pieces, I can assemble them back together to make the response of the body. That's how it works. So this breaking up, assembling is how it works. If you want to use calculus, there's one more step. You have to now allow the pieces to shrink down to 0. That's a mathematical step. That's not a physical step. Physically, you can only test chunks. You cannot test infinitesimal chunks. You have to test only finite chunks. Then you have to make a leap of faith about what it says about the infinitesimal chunk, so that you can put it back together by using calculus. And integral calculus is putting it back together. So you will use the tools of calculus and other things to do a purely mathematical version, calculus based version. If you don't want to do that, and if you want to do a finite element based version, you can see why it's called a finite element. So these pieces are called the elements, and then you have a finite number of them, not an uncountably infinite number of them. You can do a very nice job with this kind of thing. And there are lots and lots and lots of caveats as we go along. So you will see that in order to make this thing reasonable, we have to assume a lot of things about how the response works. With that, we are done. Thank you.